Because chapter 8 is new. It's just not the same kind of new. Anyway, I don't know. The calendar's up to date. Oh, no, it's not. I will get the calendar up to date. We're almost to the end of last year, and when we come to the end of last year, we need to have a big old forever quiz. And then the end of the semester, we'll have a forever endeavor final. And then next semester, we'll have forever quizzes, or endeavor quizzes, because it'll all be new. We have like 3, 4. We don't have very many. 2. I don't know. Slope fields, though. Long story short, it's not an endeavor card because we already did it. Slope fields, what's going on? What's the purpose? What's the point? Is to follow the flow. Remember that from last year? The purpose, the point is to follow the flow, and more specifically, what's a practical application? If you're dealing with a situation that is hard to model, aka hard to get an actual equation for, you can imagine it'd be hard then to anti-derive if you can't even get an equation for it. So maybe it's hard to even model what's going on, and so wind current, wasn't that it? I think it was wind current as far as like a weather map. And you were able to see, based on like the different instrumentation or the different sensors, etc., what the wind was at different points, locations, as far as the speed and the direction. And if you have the direction and the speed, you can make a slope field out of it. A vector field is another way of saying it. And then you can follow the flow, even though it would be either hard, even impossible for you to actually anti-derive and get an antiderivative function. That's like the idea behind a slope field. But as far as like the particulars of a slope field, remember a slope field is formed by slopes. And slopes could be in terms of, they could be in terms of x and y, no big dealio. Either one we can deal with, either plugging in x's or plugging in x's and y's. Particular solutions, if you have a slope field, right, you're going to follow the flow. Particular solution, aka that'd be something like y equals f of x. If they're asking you about y equals f of x, or more particularly, if they're having you match y equals f of x, remember you're following the flow through the slope field. Because the little baby slopes are just the different values of the rates, aka the derivatives. But what's following the flow is going to be the actual antiderivative function. Using integration, we know that because we would go ahead and separate the dy, thank you, sir. We would separate the dy dx, so we would actually antiderive. So we could do dy is equal to f of x dx. That's like AB stuff, right? And we haven't gotten to super hard integrals. I have no idea what it was. I don't know. I'll figure it out in a second. Oh. Interesting.
Can we please check it, Misty?
I will. I'll go get it. I'll go get it. But hold on. I want to show something real quick. To use integration, right, we have to separate the variables. When we separate the variables, we integrate both. True, true. What would you do if this were the case? We can try to anti-derive that, and some of them might be impossible, but most of them should be at least somewhat possible for us to at least visualize or you know, think about where it might have come from. But what do you do if you multiply by dx and the derivative is in terms of x and y? Maybe that's multivariable calculus inside the realm of this class, like Calc 3-ish. Interesting. But for right now, you would only be able to use integration to anti-derive if it's explicit. If it's implicit, you wouldn't even be able to. You can double integrals, etc., if you're curious, and multivariable calculus, what's different. But coming back, determined by the highest order derivative in the equation, that has to do with the actual order of the differential equation. Did I even write differential equation? Oh, I did. We're defining a term up here. Differential equation is when you're given an equation of derivative, whether explicit or implicit. If there's only y primes, we would call it a single order differential equation. If it's y double prime, we would call it a double order differential equation. You could also call it a first degree, second degree. You could do that as well. A single order or double order. degree. But that has to do with what derivative, not specifically like the actual degree of the differential equation. And there is a class called ordered differential equations where you just focus on them. I would love to tell you what that class is about, but my teacher kind of broke his hip at the beginning and would just kind of sit up there and tell us about his dissertation the whole time. We did homework, but I don't exactly remember what the point of the class was. Students that have gone had a very different experience in that class. Anyway, it's about differential equations, and you're doing things with them and applying them, but that's about all I got. His dissertation was on the reproduction of frogs. I remember that much. Anyway, doesn't really help you at all. But single order, double order, differential equations. Hey, these are interesting. Have we seen something like that before? This one, y double prime minus y equals 0. What's going on? Is that a differential equation? Yes. Why? Because there's a derivative in it. Oh, Isa.
Oh, I've been holding my breath for like 10 minutes.
Yeah, it's for tardies.
What?
No, go talk. Go talk to them and try to figure out what's going on. Oh my goodness. Guilty conscience?
I don't know, Mr. T doesn't mark me tardy, but
Mr. T doesn't mark anyone tardy. It's kind of crazy.
I already have 3 tardies. You didn't either. It's so annoying.
I'm tardy every single day.
Okay, so coming back. It's a differential equation because there's a derivative in it. But what kind of differential equation? What would you actually name this? It would be a second order differential equation. How would you solve it? Add the y and make it a d squared y over dx. Don't. We're not solving it. At least not right now at this level. What are we doing instead? If they ask us which of these or are any of these a solution, you guys have seen this on AP type questions. If they say which one matches, what can you do? Can you work forwards, aka solving from the second derivative, anti-deriving a lot back? How would you do that? Maybe, but couldn't you also work the other direction? You guys have gotten to a multiple choice question before where you've worked backwards, right? How can we work backwards? Plug in. Sure. Y double prime minus y equals 0. Y double prime minus sine equals 0. I don't know. Oh, wait. What else do you need to do? Can you do mental math with derivatives? What's y double prime? Negative sign. Good. What's y double prime of 4e to the negative x?
Oh, it's just
4e to the negative x.
16. It's 16.
Or it's just 4e to the negative x.
Oh, wait, I screwed that up.
It's the same thing. Yeah, because the negatives cancel.
Because it's going to be 4e to the u times u prime, and then 4e to the u times u prime, and negative times negative is a positive.
And that's the same thing.
What's y double prime? Mm-hmm. Because it's not a u, it's just going to be the same every time. So which ones make sense with that? B and C only, right? So if you were to see a higher order differential equation than just a single, aka if you were to have a higher derivative, I'm telling you right now, you want to work backwards, you don't want to work forwards, because we don't have the training, the skills, in order to be able to do it. And if you're curious as to what I mean by that, if you were to try to solve this, and you could probably finagle your way around to play with it, in that, if you're talking about a derivative subtracting an original function being 0, it's going to have to be an exponential or trigonometric function. Why? Only exponentials and trigonometric, when you derive, either are or soon will be in the same form. Specifically, just sine and cosine, not tangent or cosecant, because as soon as you start deriving those, they're going to be in a different form. So we kind of know it has to be exponential or sine or cosine, which is why they use those as examples. But if you were to try to solve this, do you see what I mean? If we were to multiply that on the other side, we can't integrate a y with a dx and a dx squared. That's even worse. Well, we could think about this as being maybe like a d. I'd have to redefine it. But we could make like dy dx equals, I don't know, to do something like dA dx equals y, and then maybe we could go ahead and get back to an ln, and then we could go ahead and, but it just gets bad. Meaning our math is insufficient. Our skills in calculus are insufficient to solve that with what we know right now. But we can go backwards. Okay, moving on. Could you actually solve this guy? What I mean by solve is getting back to a particular solution, aka getting to a y equals f of x. Could we get to a y equals f of x from this equation? My answer is yes, because it's a single order. My answer would be yes, because it's a single order. However, that's not specific what they're asking. They're actually saving us that. There's a question on your actual test from the differential equation chapter similar to this, very similar. In that I gave you kind of what the solution was and then had you plugging in a clue, an initial condition. But a lot of you guys did all the work to get there, sadly, and wasted tons of time and then plugged in the initial condition instead of realizing they've already given it to you. Now in this one, they're saying verify it's true first. And then once it's true, you don't have to necessarily solve to get there. You can go ahead and then use it. How can you verify it's true without solving it? Work backwards. So x times y prime minus 3y equals 0. I mean, what's y prime? Work backwards and say, oh, okay, well, y prime is, does it work? Well, if I plug in x times 3x squared, sorry, there's an awkward parenthesis. I don't really know why, but that's okay. Oh, it's a c. I forgot there's a c. It looked like a parenthesis. Lo siento. Okay, thanks, good. Does it work? Uh-oh. Is this true? Oh, dear. Yes, it is. It took a long time for us to say it. Isn't that 3cx cubed minus 3cx cubed? Isn't that true? Okay. So does this work? Yes. And since it works, you're like, okay, cool. It must be a solution. Okay, cool. If it's a solution, find the particular solution. You have to necessarily solve, especially this choice. All I have to do is say, okay, cool. I have a clue. My clue is going to be y is 2 when x is... Plug it in, plug it in. We end up with negative 2 over 27. It's okay. So then what's my particular solution? You guys know the wording, right? Are they looking for this? No. What are they looking for? No, you're right. Yeah, they're looking for the whole equation. But in case you're curious, I did say that you could have solved this. And how could you have solved this? Couldn't you have made it x times dy dx equals 3y? And couldn't we have rearranged that to be dy over y equals 3x dx? Can you integrate that? You can integrate that. So if it's a single order, where it is possible, now careful, remember there are some impossible integrals for our level of math where we're at, or our level of calculus, I should say. If you can get all the y terms with, or multiplied by a dy and all the x terms with a dx, that's totally possible for you guys to integrate. That was not the point of the problem. The point of the problem was like, hey, look, this is a solution. Get particular. I'm like, okay, cool. How does this apply to slope fields? This is an equation that could define slope. And as soon as you have a differential equation, that can form a slope field because it can define slopes at points at x's and y's. And then the particular solution flows through. And remember, a slope field, if you establish a point, doesn't it pick a particular flow? So that's how we're going to relate it. Slope fields, fields of slopes, formed by differential equations. Single order. Well, for our purposes, single order only. So to make a slope field, we need a differential equation. We need some sort of representation of the slopes. It's a graph showing a family of anti. Remember, it's a flow, so there's going to be a lot of different options. And to be honest, there are complicated differential equations that are going to show flows or antiderivatives that behave differently at different points. So depending on the initial condition that is met and the complexity I shouldn't say complexity. How involved the differential equation is. 1 second it could be acting like a cubic, the next second it could be acting like an exponential, the next second different initial conditions. So we in our minds are only thinking of simple differential equations when we think, oh hey, vertical shifts, that's it. Well yeah, the simple polynomial ones, they'll just be vertical translations, family of antiderivatives. But of more complicated differential equations, ones that theoretically that we actually can't solve right now or maybe ever, those ones, the initial condition is very important because the entire behavior could change. A family of antiderivatives doesn't mean everyone in the family looks the same. It depends on the flow. Just because they're a family, sometimes they all look the same, just they're shifted, and sometimes they look very, very different. What's the purpose? To provide a visual perspective of the original function's graph. I guess you could do apostrophe S. Because for any differential equation, we're only talking about, well, the whole family, they look different. I'm going to keep it with S apostrophe. I think it's more correct. So you're going to be given some sort of, I'm going to say dy dx equals, or some sort of y prime is involved. It could be isolated or it could not be isolated, but it's providing a visual perspective for the original. And I think you guys have already written follow the flow, but you could go ahead and put follow the flow here as well. So our way of remembering it last year is that these guys defined the baby tangents, specifically the baby tangents slopes. And this guy was the flow, as far as the matching clues with the AP questions. Just quick reminders. Differential equation defines the baby tangent slope, and then this guy follows the flow. Now, here's a dilemma of these examples. Is it easy to get these examples down in your notes? No. So it's up to you as to what you write and how you write it, but I would like some sort of representation of what we're doing. I'm going to try to not give you too many actual slope fields for you to sketch, but maybe you can at least get the idea. What's more important is the wording and what you do as a result of the wording. Does that make sense, guys? Important is the wording of what's being asked and what you do in response. So it's kind of up to you as to what you write, but we are going to do some examples now. A few of you might have still been writing, depending on how much you thought you needed. So let me go ahead and do that. Okay, example number 3. Sketch a slope field for the differential equation. Y prime is equal to x minus y for the points -1, 1, 0, 1, and 1, 1. Okay. What do I have here? The entire slope field. What was actually being asked up here. This slope field is the one that's defined by this function. This function is an implicit differential equation, an implicit first order differential equation, aka this is one that we could not solve by hand, because if we multiplied the dx, this minus y is trapped. So we can't solve with our level of calculus right now. That's okay. And y is, why are all of the slopes horizontal along this line? What's going on right here? What's so special about this line? Why are, yeah. What's 0? This is 0. Why? Because this line is what line? Y equals x. Good. That was only if you're matching, though. But what's going on at -1, 1? If you were to plug in -1, 1, then you would have -2. And so at the point -1, 1, there is going to be some sort of, what do we have? I think we're going by half tick marks. That's kind of a guess on, that's a bit of a bummer. But we do have a negative slope and a fairly negative slope, right? At 0, 1, what's going on? Slightly negative, but a little bit less. And at 1, 1, what's going on? Ooh, I should have gone this way. I apologize. I said we're going by halves, and I didn't go by halves, so that'd be negative 1. Negative 1, 1. There we go. And then 0, 1. There we go. And then 1. Question, are all three of these points on the same particular solution? Because this one, you would follow the flow of the slope. You wouldn't go horizontal, right? Wouldn't you go curved down? So each of these defines a different particular solution. However, each of them are, each of their slopes are necessary for the entire slope field. So the difference between making a slope field, we can use 3 different points that are from 3 different particular solutions to find slopes to start forming the entire field. But if we were talking about particular solutions, each of these would have a different one. Does that make sense? Okay. This is a little bit more AP. What if they were to give you, hey, y prime, that's a single order differential equation. They give you a point, an actual point that's on the particular solution. First question just says, find a slope field given that differential equation, but they give you set points. So someone who did it last year and somewhat remembers how we make slope fields, how would you take this differential equation and put baby tangents to see at least kind of what the flow looks like? And actually, it's a little bit nicer because do you have to plug in the x and the y? No, just plugging in the x is sufficient, which is nice because then if you go to something like x negative 1, plug in when x is equal to negative 1, what does my y prime end up equaling? 1/3 plus 1/2, which is going to end up equaling what? 2, 6 plus 3, 6, 5, 6? Anybody with me? Okay. So 5, 6. Go ahead and for this x value, stink, 5, 6. Well, isn't that just a little bit less than 1 if worst comes to worst? Because I don't have an up 5 over 6. But I could go up almost 1 and then put a baby tangent. And the nice thing is I can copy that for all 3 of these because all of their x's are the same. This whole vertical pattern of an entire vertical line copying or mimicking the slopes is always when the differential equation is dependent only on x specifically. Because if it was dependent only on y, what would we see with our slopes? The horizontal line would be the same. And when we have x's and y's, we have this issue where it's not the same horizontal or, I should say horizontally or vertically. You guys have already plugged in for 0, right? Isn't that flat? For 1, we would end up with 1/3 minus 1/2 or 2, 6 minus 3, 6 minus 1/6. So it's not going to be very minus at all. Because if that's 1, down 1 over 1. 1/6 is a little bit less. Anybody plug in 2 yet? 4/3 minus 1. 1/3? Positive. Why does that kind of make sense that it goes positive so quickly? Oh, sorry, plugging in 2 for x equals 2. That would be 4/3, right?
Yeah.
Minus 1. Yeah, so positive 1/3. Why does this flow kind of make sense just based on us seeing this differential equation? If the differential equation is a quadratic, what does it have to come from? Ooh, if the differential equation is a quadratic, what does it have to come from? Cubic, right? And then using integration, if they do ask this one, quick reminder, we would go ahead and it would be legal. This one would, not all. We already saw that would be impossible. But can we solve this one? Yeah. We separate the dy dx, and then we have a model where we can integrate. And then we'd be able to go ahead and find that our actual particular one would be what? X cubed over 3, so 1/9. X cubed minus 1/2. X squared over 2, so 1/4 x squared. Let's see. Let's see. How do we make this particular? We plug in the point. How do we make this particular? We pick the point. And if we pick the point and follow the flow, when it passes this vertical line, it's going to have to, it doesn't have to connect. That's opposite. It needs to be a flow. It needs to be a curve. So smooth curves kind of going through the slope field. That's what we think it is. But if we were to actually plug in, we could say 1 is equal to 1/9 minus 1/4 plus c. So c is going to equal, do we have to go to 36? Is there anything else? Yeah, so we have 36 plus 9/36, which would end up equaling 41/36. So both of them show particular solutions, but one is very algebraic, and it's only possible if we can actually do this step of anti-deriving. And the other one, we just had to plug in numbers and get little baby slopes and say, there he is. Which one's more precise? Of course, this one. But this one required you being able to anti-derive, right? Ooh. Given something like this, and they say match the differential equation to the specific solution. Are we going to? No. Hopefully in an educated way. Question. Are we doing baby tangents and actually looking at the slopes, or are we looking at the flow? Yeah, because these are particular solutions that flow through. Which one? Why E? It has to be E. What's the flow?
Yeah.
Pick a point.
Yeah, E.
Pick a point. That's logarithmic, isn't it?
Yeah.
Ooh. Does it make sense, though?
Laughing because I screamed. I was like,
Oh, no.
E.
Yeah.
Oh, I thought it was
I
E.
said E, but I meant
Someone
E.
said-
I meant E to the next one.
You guys didn't, that wasn't easy?
You don't know our basic graphs.
Oh, E to the back.
You're following the flow. I heard E, and then, yeah, I did think you said E. You said B. In my defense, B and E sound very similar. Oh, my goodness. What about this one?
Oh, that's absolute.
C.
Oh, this was on the.
Wait, I was about to say absolute value.
Follow the flow or slopes?
We did this practice.
Slopes, because they're dy dx's. Do you see how anytime x is 0, the slopes are flat? So 0, x has to be on top. Oh, bummer. They all are. Oh. Whenever y equals 0, the slopes need to be undefined. AKA, y better be in the bottom. Well,
Yes.
what do? You go to a quadrant, you pick the signs, because some are squared, some are cubed. You have to go to the quadrants and test the signs. Let's see how starting homework goes with slope fields, but don't worry, it's not due until Friday. Bye, guys.